Friends, welcome back to this online class. We were studying about heterocyclic compounds. Today, let's study about pyrimidine, purine, and azepines. According to the syllabus, we are going to study about synthesis and medicinal uses of these three compounds. We are not going to study about chemical reactions. First, let's study about pyrimidine. Right, as you can see on the screen, pyrimidine is a six-membered heterocyclic compound with the two nitrogen atoms as heteroatoms. So those nitrogen atoms are at one is at position 1 and the second nitrogen is at position 3. Like these two nitrogen uh, heterocyclic compounds containing two nitrogens, there are many of them. They are all called as diazenes. They're called as diazenes. In this structure itself, six-membered heterocyclic ring itself, there is one. If there is one nitrogen here, the second can be here, right? Here there can be one more nitrogen. If there is one here at position number 1, at 4 there can be another one. Similarly, that the nitrogens can be in two ring structure, three ring structure. So there are many diazenes among heterocyclic compounds. And this heterocyclic compound, the pyrimidine, is aromatic in nature. It follows all the rules of aromaticity. So it is an aromatic compound. So next, let's go to the synthesis of pyrimidine. First method is from malonic acid. It's a condensation reaction in the presence of base. So OH minus, right? Malonic acid reacts with the urea, and in the presence of base, you are going to get barbituric acid. These are the two forms of barbituric acid. One is keto form. This form is keto form, right? This is enol form. These are the tautomeric forms of barbituric acid. They are isomers. So this is a tautomerism, right? It's a structural isomerism. Anyway, this keto form of barbituric acid gets converted to enol form of barbituric acid, and this enol form further reacts with the phosphoryl chloride, right? By reacting with the phosphoryl chloride, it's going to give the chlorine substituted product. So this further with the treatment of zinc dust in hot water, it is going to give pyrimidine. So this is the first method of preparation of pyrimidine. The second method is from 1133 tetraethoxypropane. This is your propane, right? This is your propane. There are two ethoxy right, two ethoxy groups are here, right? So it is 1133. This is position 1, this is 2, and this is 3. So it is 11, right? 1133 tetraethoxypropane, and that is going to react with the formamide in the presence of aluminum trioxide or alumina at 200 degrees centigrade, and you are going to get the product pyrimidine. Next, we will go to the importance of pyrimidine. So the pyrimidine is widely present in nature. It is also the building block of nucleic acids, ribonucleic acid, RNA, deoxyribonucleic acid, DNA, some of the viruses. So there are DNA viruses, there are RNA viruses too. And these pyrimidine bases, actually there are three pyrimidine bases, right? Those are like cytosine, uracil. Okay, there is one more pyrimidine bases, that is thymine. So that is thymine. Right. These cytosine and uracil are present in RNA, and this thymine is present in DNA. They are present as nitrogen bases. So they combine with the sugar molecule, and then again that combines with the your phosphate. So that will make that a backbone of your DNA or RNA sequence. So in RNA you have a cytosine and uracil, right? In DNA you have a cytosine and thymine. Right. So this our the problem we are dealing with now, that is coronavirus. It's a RNA virus. As you can see the structure here, I have explained this structure before. So you have a spike protein, right? These are the spike protein with the help of which they can enter our body, and this is the lipid membrane. This is the lipid membrane, and inside that you have the RNA, the nucleic acid, and this with the help of RNA they multiply. So this RNA is going to replicate, and because of that replication, so it is going to multiply and spread. Right. So let me in this structure with this spike protein, it is going to enter our body, right? So it's trying to kill us, and we are also trying to kill it by rupturing its membrane by washing our hands with soap, and also by sanitizing our hand using hand sanitizers. We can also rupture that lipid membrane and kill the virus. So inside the body, if we have to kill, we have to what we have to do, we have to replace these nitrogen bases using a similar medicine, using a medicine with the similar structure as that of nitrogen bases. So that is how we can kill these viruses. So one more tip let me give you here. They say do not touch your uh, nose, mouth and eyes. So why do they say that? This virus, it cannot enter our body through the skin. That is because the epidermis, the upper layer of the skin, it is thick enough for the virus to enter, but it can enter our body through nose, mouth and the eye, because mouth and nose, these are mucous membranes. They are very thin. They are made with very thin mucous membranes. These viruses can enter through this. It can also enter through the eye, even the cornea or sclera. They are very thin, and it can enter through uh, that also. So that's why we should not touch our mouth, nose and the eyes. So the wearing the mask will protect us from these from touching this mouth and nose. So that's why it's good to wear the mask for this reason. And also mask will help you if the patient or the suspect coughs on you or sneezes on you. It will prevent droplets falling on your nose and mouth. So that's how you can protect yourself from mask from this coronavirus. Alright, let's go to the next section. So pyrimidine ring is also present in thiamine. Thiamine is a vitamin B1. Vitamin B1 is required for metabolism inside the body. Um, Thiamine or the vitamin B1 deficiency will cause the disease beriberi. So this pyrimidine derivative is also present in alloxan. Alloxan is a chemical which can cause actually diabetes. This alloxan, it kills the beta cells of Langerhans of pancreas, thereby it causes the diabetes. It is used in the lab animals to induce the diabetes. So next, let's look at medicinal uses of pyrimidine. The first um, group of drugs is barbiturates. You have the examples of phenobarbital, pentobarbital, and secobarbital. So this is the structure of phenobarbital. Right? You have the pyrimidine ring over here, right? So it is used as a sedative and a hypnotics, that is to reduce the anxiety, and it is also used in certain types of seizures. So seizure is convulsion, right? Involuntary convulsion. If there are more than 3 seizures in a day, so that can be called like epilepsy. So it is used in epilepsy. Alright, next is sulfur drugs. Sulfur drugs are sulfadiazine, sulfamerazine, sulfadimidine. So these are the sulfur drugs which contain pyrimidine structure. So when this moiety is present, like sulfonamide moiety, then they are called sulfur drugs. So here is your pyrimidine ring. So this is the structure of sulfadiazine. Sulfur drugs, they are used in as antibacterial agents. So they are used in urinary tract infection, ear infection, meningitis, and malaria. Alright, this is about pyrimidine. Let's study about purine. Purine is, as you can see, two-membered heterocyclic ring, right? In that one ring is the compound which we just studied, that is pyrimidine, right? With the 2 nitrogen at 1 and 3 position. And the second ring is imidazole, which we also studied in 5-membered heterocyclic compounds. So this purine is aromatic, so it satisfies the rules of aromaticity, so it's a aromatic compound. Next, let's study about the synthesis. First method of synthesis, that is from 4,5-diamino of pyridine. You have position 1, 2, 3, 4, 5, and 6. So this is your pyrimidine, right? This is pyrimidine, and for the pyrimidine you have attachment of amino group at 4 and 5. So this is 4,5-diamino pyrimidine, and you have to make that react with the formic acid, and there is going to be removal of water. It's a condensation reaction. Here there is one molecule of water, and here there is another molecule of water, and you are going to get purine as the product. And next is second method from uric acid. So this is your uric acid. So again there is a tautomerism here. Uric acid, it is in keto form, right? It will get converted to alcoholic form, so it is enol form, right? It is uric acid in enol form, that you are subjecting to phosphoryl chloride, so you are going to get the chloride substituted product to 268 trichloropurine, right? You have to subject that to hydrogen iodide at 0 degree centigrade. You will get the iodinated product 2,6-diiodopurine. So you have to pass that over the zinc dust using hot water or the boiling water. So you are going to get purine as the product. So that is the second method of synthesis. Now let's go for the importance of this purine as discussed earlier. So it is there in nucleic acid, both in RNA and DNA. Here there are purine bases. One is guanine, the second one is adenine. So these are there in both in RNA and DNAs. So to kill the virus, or to kill such organism, the harmful organism, what you have to do is you have to uh, change this, you have to replace these purine or pyrimidine bases, and such drugs can kill these viruses or bacteria which cause harmful diseases. Right, next in the importance, purines occur in nature. So the other products which you can find in the nature are uric acid. Uric acid is there in our body. It is also available in the nature. So xanthine is also there in the body. Then caffeine, which is there in our coffee, tea. So that is also a purine derivative. So among the medicinal uses, first one is nucleoside anti-metabolites. So they are anti-metabolites are the one which replace this purine nitrogen bases. So examples are acyclovir and valacyclovir. This is the structure of acyclovir. You have the purine ring over there with the substitution. These antiviral agents, these are antiviral agents, right? Acyclovir and valacyclovir, they are antiviral agent which can kill the viruses. So they are used in chickenpox. The acyclovir used in chickenpox, and chickenpox is caused by varicella zoster virus. Right, chickenpox. You might have seen this chickenpox as the red bumps all over the body or the blisters all over the body. That is the chickenpox. It's treated. It is treated with the acyclovir. Then cold sores. You might have seen this also. The blisters on the mouth, blisters on your lips. So they are signs of a cold sores caused by herpes simplex virus. So acyclovir can treat that. And genital herpes, it is a sexually transmitted disease which is caused again by the virus and treated by acyclovir. So next set of medicinal compounds are methyl xanthines, caffeine, theophylline, and theobromine. So these are stimulants, right? These are CNS stimulants. They are used in bronchial asthma. They are bronchodilators. So these are the uses of these methyl xanthines, caffeine, theophylline, and theobromine. This is the structure of theophylline with the purine. It is a purine derivative, or it has got the purine ring on it. These compounds, methyl xanthines, they are also diuretic. Alright, that completes the purine. Let's study about azepines. As you can see on the screen, this is one of the azepines. They are called azepines. So there are a set of azepines. So this is one azepine. So this This is actually 1H as a pi. The numbering 1, 2, 7 numbered ring, 3, this is 4, this is 5, this is 6, and this is 7. Right, this is 1H as a pine. It's a poly unsaturated 7 numbered heterocyclic ring with one uh, heteroatom, that is a nitrogen. Right, it is non-aromatic. It does not follow it will not have the required um, electrons that satisfies the Huckel rule. That's why it is not a aromatic compound. It is non-aromatic compound. So how will it react? So it follows the reactivity of cyclic polyenes. Polyenes with the double bonds, right? These are polyenes. It is a cyclic polyene with these are all double bonds or dienes, right? The cyclic polyenes, the other cyclic polyenes, it will follow the same reaction um, similarity with the other ones. So next, these azepines, they show tautomerism, right? Tautomerism is nothing but difference in just hydrogen um, atom presence, right? So this is one tautomeric form. It is 1H azepine. These are the other tautomeric forms. 2H azepine, as you can see here, if this is 1, this is 1H, 1, 2, 3, so I already numbered them, 4, 5, 6, 7. So in that, this is 2H as a pine. At position number 2, you have two hydrogens, and there is no double bond over there. So that's why it is 2H as a pine. If it is at position 3, it is 3H as a pine, then 4H as a pine. So these are the tautomeric forms. In this, the most stable is 3H azepine, and this is the only tautomeric form that exists actually. The other ones, the 1H azepine, 2H azepine, and 4H azepine, they do not occur. They are very unstable. Only 3H azepines are stable, and you can isolate these 3H azepines. So here the order of stability: 3H azepine, then the next stable compound is 4H azepine, and the next to that is 1H azepine. But these two you cannot isolate. Only 3H azepines can be isolated. Alright, next is the synthesis. The first method of synthesis is valence bond isomerism. Valence bond isomerism is just the reorganization of sigma and pi electrons. There is much transfer of these groups and atoms. There is no much transfer of those, but here there is internal rearrangement of sigma and pi bonds takes place. So you are taking here benzene, and you are making that react with the ethoxy carbonyl nitrine. So this is your benzene, right? This is benzene. This is ethoxy, right? This is ethoxy group, and this is carbonyl group, right? This is ethoxy carbonyl, and this is nitrile. This is nitrile group, right? And you have to subject this sunlight to this or UV, right? You have to subject to UV. So the nitrogen gas is going to get removed. So what is going to happen here? So these two will react, and this is the product going to form intermediate product. So one is with this, combining these two, so you are going to get the nitrogen, and this is going to go here. These two bonds, the two bonds over here from the nitrogen, between nitrogen, first nitrogen and second nitrogen, two bonds, so they are going to form bond here. right, with this ethoxycarbonyl nitrile. So that is the intermediate product, and then you are going to get an ester, n substituted ester. So you have to subject that to a basic condition. Along with the heat, you are going to get 1 azepine or 1H azepine, and isomerism takes place, and 3H azepine is what you're going to get. As I have told you earlier, 1H azepine is very unstable. It isomerizes to 3H azepine, and you can isolate this 3H azepine. That is the first method of synthesis of azepine. The second method is from nitrobenzene. So in this formation of 2-alkoxy 3H azepine. So this is the substituted product of azepine. So this is the nitrobenzene. Nitrobenzene, you have to do the dehydrogenation using, you're going to remove this, sorry, deoxygenation. So you're going to remove this oxygen from here using tributyl phosphine. This is your tributyl phosphine. So you are removing this oxygen. So the two electrons are going to be here with the nitrogen. Right now, what will happen? You have to use alkyl alcohol. So you're using alkyl alcohol here. So that is going to form OR bond over here, alkoxy bond over here, and this double bond from here going to shift over here. As you can see, it has formed a bond over here, right? So that is going to be uh, forming the bond here, and that should form a bond here. Totally, ultimately, with the again with the presence of acid, so you are going to get 2-alkoxy 3H azepine. 2-alkoxy 3H azepine. This is position number 1. This is position number 2, 3. Right. So this is alkoxy group is at 2 position. It is 2-alkoxy azepine. That is what you are going to get from this reaction. So next is the medicinal uses of these azepines. The first one is anti-convulsants. The examples are carbamazepine and oxcarbazepine. Right, here is the structure of the carbamazepine. So here is your azepine ring, right? Azepine ring with the two benzene rings attached. So these are used to prevent and control seizure, right? And it is also used to relieve certain anxiety disorders. They are also used in anxiety disorders. The second use is they are in the azepine rings are in tricyclic antidepressants. Examples are imipramine, desipramine, and clomipramine. So this is the structure of imipramine, right? With the azepine ring with the two benzene rings fused. They are used in depression and certain anxiety disorders. So that is the uses of these tricyclic antidepressants. This completes these three compounds, right? Pyrimidine, purine, and azepines. Thank you very much. And actually, we have finished the heterocyclic compounds. Okay, that finishes the heterocyclic compounds. And let me know if you have any questions. Thank you very much.